equation with the fxp, the quasi-probability distribution, which is really the density matrix. It's a density matrix in a different.
Which means that you get two equations for the p double bar, and this is the same as having a Schrödinger equation.
So you think that were your remark supposed to mean that he's making a result?
No. My remark is what. So I mean, he has this f is sort of this probability density, which is not on probability density.
It's a density matrix.
And then I mean
you concentrate.
You go to the margin of it. You integrate out all the p's. You take the average of p over the p, so to speak, and then you get two equations which is the same as having the Schrödinger equation, which means that it has the same content, which is sort of surprising.
But there is also an old way of deriving Schrödinger equation out of a current you saw, and continuity equation you saw as well.
Yeah,
it's the same thing, but
so it's that. So I mean, you get the equation for the current, for the probability curve, and for the
So it's very similar. It's backwards a little.
Yeah.
But at the very end, it looks very close to Madelung's derivation.
Yeah, but it's there. Yeah, but it's, as you say, it's backwards. But the point I think is important is the way I come to it.
I understand this. I understand.
Sorry,
but I just wanted to talk about the structure of the thing.
Yeah. No, I'm still going to.
I mean, so the speed double part is double by you thinking of sort of the average momentum over an ensemble.
Of an ensemble momentum, if you want to look at it that way, yeah. And then this is the way you get the phase space, because this p is not the eigenvalue of the momentum operator. That's why you can get these phase spaces. That's why you can get the Bohm trajectories. And for people who haven't seen the Bohm trajectories, I always flash this on. I'm glad I put it in. I very nearly didn't put it in because I'm so bored of the wretched things. But people want me just to say a little bit about what they are. This is the two-slit experiment, and these are the ensemble of possible trajectories working, integrating that equation. So we know the solution of the Schrödinger equation, we take the S, we just calculate that, and these things come out.
And these trajectories do not contradict the welcher Weg.
No, I've got two papers coming out with Bob Callaghan, which actually, as you know,
I'm sorry, do not contradict what?
the vacuum egg. They've got it wrong, they don't understand the Bohm theory.
Getting information.
You can tell which way, right?
Yeah.
Scully is not coming in, huh?
Yeah. He's not coming here. No, he's a nice guy actually. I met him in. No, he's not like Shelley.
No, we met him in Berkshire last year.
Oh yeah, you don't like him, do you?
Scully.
I won't say what you say about him because he likes Bush.
Oh, Bush is a nice guy.
No, but I drew because we've been having an argument about the vacuum egg, as you probably realise. And I then drew these trajectories on where he's made an absolute arse of himself. I managed to trap him in a room, just him and me. And when I drew, we couldn't quite get started on how we should discuss this problem. And then I just do these two things with trajectories crossing. And he said, oh, yes, well, I must go now. So I think he suddenly realised that he had... Because he said, because the number, what was it, the current, you see, you've got a situation, sorry, I shouldn't really be doing this.
Can you open it, because then you can see, if you're not sure.
Well, I don't know, can you see, George? Suppose you had this two independent sources here rather than a coherent source. Then you know the particles would go this way here, and the particles would go this way here, right? And there's a line of symmetry there. And his argument is, because you see these things here, they never cross. Okay? And that's the whole vacuum Weg is based on that assumption that trajectories never, but they do. Take an independent source here, and an independent source here, and they obviously cross, they just spread out. Right? Now then, what he did was to calculate the current J, Z from the top slip, add together the current from the bottom slip, found it's equal to 0, by symmetry. Of course it's equal to 0, but then he concluded, therefore, no trajectories cross this line of symmetry. That was the fault. I mean, how on earth he came to that conclusion, I just don't know. And that's what I say, as I drew this up showing the things crossing, he suddenly said, oh, I must go now. So I don't know whether he's accepted it. I know he must accept it, I mean, it's so obvious. That's a mistake they've made, do you realise that? Anyway, so that's the Valkyrie Weg. Once you allow for those situations, you then have got to say that when you've got the cavity in the Valkyrie Weg device,
Maar de
makes it-
Belgische week.
Eh?
Belgische week.
oh, right. Are baichi am tungkoi tapper denga to nacho brow.
I was thinking we're talking about somebody who had written a paper.
Sorry.
Sorry, I didn't say anything.
No, I just got my own back by swearing at you in the start. And then you've got the barrier here and you see why particles go through and so on and so forth.
Well, that's the whole thing, there's a bit of the Germans.
Anyway, what Moyal didn't do, of course, was to ask what the other marginal did when you integrated over P rather than integrating over X. And find X double bar. And look what you get, Morris. Remember the minus S grad P, the grad PS that I got for the second equation? It's just it. And then you get another, the transport equation in that case is just the Schrödinger picture, the Schrödinger equation in momentum space.
Sorry, what was the first one? So we find in the...
Oh, this is, instead of P equals grad S,
Ah, okay, yes.
you replace it by saying X is equal to grad P, the minus sign. And this is the one that Shelley Goldstein went bananas on, because he didn't want to believe it existed. Okay. Oh, and this is just to say, this comes to the blob again. What this X and P are in this quasi-probability distribution are just the mean, but if you think of a blob in phase space, and you look at the mean value of the blob and you look at the difference of the blob, then your this distribution function is just the density matrix in these variables. So you're not doing, your phase space is non-local right from the beginning. Right from the beginning. So you're dealing with blobs all the time. I don't know how this works.